Today I'm going to talk about one of the most useful edge detectors, which is called Canny. So Canny takes as an input the Sobel's output, which is the gradient magnitude and direction. Now the first process applied in Canny edge detection is called the non-maxima suppression. Non-maxima suppression. And what that is that for each pixel on the gradient magnitude map, we should evaluate a number of neighborhood pixels across the edge. And if this pixel, the subject pixel, is the maximum one, has a maximum value, then we should just keep it. Otherwise, we would set it to 0. So this is an illustration of what I just said. So this is a gradient magnitude map image, and let's say that I have an edge that is shaped in the form of an arc. And let's consider that this edge is like 3 pixels thick. Now what I would want to do is to take a given pixel, for example this one, and see its neighbors, evaluate it with its neighbors across the edge. And the direction across the edge is given by this vector. So this is across, and this is along. So this across direction can be got using the gradient direction. The gradient direction always points perpendicular to the direction of the edge, so it points across the edge. So as I said, I should evaluate this pixel with a number of neighborhoods across this edge. So if it has the maximum value, I should just keep it. Otherwise, I should set it to 0. And in this way, I would get an image that I would call the non-maximum suppression image, and it would be made out of edges that are 1 pixel thick. Now the reason why this works is simple. So let's just consider that I cut across that edge and want to see its shape on this side. So what I would get is just an impulse like this one. So we have already seen that when we did the first derivative of an edge. So this is actually just looks like the one-dimensional first derivative. And what we would do is, as I said, just take one pixel on across this edge, in the direction along which you are evaluating the neighborhood pixels is this one. This is the direction across the edge. And of course I would get this pixel here as the maxima. So this is the maxima, local maxima. So the result in the non-maximum suppression image would be just this intensity level, the same intensity level, and everything else, all the other neighbors, would be set to 0. Now the number of neighborhoods to use in that evaluation would be dependent of the size of Sobel. Just because the Sobel kernel, and this is because when the Sobel kernel, the size of the Sobel kernel increases, the edges get thicker, and in this way we would need to evaluate more neighborhood pixels. So that's it for the first process. Now the second process is called the thresholding, hysteresis thresholding. But before talking about hysteresis thresholding, let's just talk about thresholding. So one thing that we can do with this non-maximum suppression image is to threshold it to get a binary image. So I can, for example, choose a given threshold. So I can say that this is the threshold I'm gonna use to get my binary image. So this is the intensity level. Intensity level. So everything that is higher than this threshold would be an edge, and everything that is lower or equal than this threshold would be non-edge. And in this way we can get a lot of real edges that are 1 pixel thick as we want. But the problem with this simple thresholding method is that we in practice have edges whose response is small. So in this way they may not make it to the final edge map. So one thing that we can do to resolve this problem is to reduce that threshold and make it here, for example. So in this case we can get those weak responses, we can get those weak edges, but the problem here is that we would also increase the amount of noise, and this is not something that we would want to get. So given that problem, Canny come up with a solution called hysteresis thresholding. And what that is that instead of 1 threshold, we would use 2 thresholds. This is the threshold high and threshold low. So the way by which this hysteresis thresholding works is simple. So here, everything that is here is an edge, and everything that is here is directly considered as a non-edge. And the pixel intensities that have this a value, this interval, are subject to consideration. So this consideration is to check if a pixel that has a value in this range is connected to an edge. If it is connected to an edge, then we consider it as an edge. Otherwise, we consider it as a non-edge. Quite simple. And the reason why this works is because weak real edges tend to be connected with real edges. So let me just bring a pen to explain a simple idea. So if I take an image of this pen, for example, so what I would get is a very strong response on this edge here, on this border. And the reason why I would get such strong response is just because there is a high contrast between this the color of this cap and the background, which is the paper. So white and black, so the response would be very high. On the other hand, the response on the body of the pen in this region on this border would be much weaker, and the reason why is just because it is white and the paper is also white, so the contrast between this object in the background in this region is very small, so we would get a very weak response of the edge across this border. But if we choose these two thresholds properly, then this edge would make it to the final edge map, just because it is connected to a very strong edge that would definitely be considered, would have a response that is higher than this high threshold. Another reason why this works is because the noise is usually not connected with any real edge. Therefore, when we perform hysteresis thresholding, we just filter out this noise. And this is how the Canny edge detector works.